Now that you've made some sense of geometric patterns, let's try to delve into the arithmetic patterns a little bit. In letter B, it specifies that there must be an arithmetic pattern that connects you from 2, which we'll call the first term again, all the way down to the fifth term of 162. That's quite a jump. And because it's arithmetic, that means we must be considering adding some terms. So 2 plus something plus something plus something plus something is going to give us an eventual 162 if the pattern continues. So just like we did before, let's take some time with a little bit of an awkward silent pause to think about a possible pattern. Think about any sort of strategy that might help you figure out how to make this task easier. Because guessing and checking numbers might not necessarily be the most efficient strategy. Although if you have a calculator, it certainly might work. Think about, though, how many jumps do you need to make to get from the first term to the fifth term? How many additions will you have to do? And if you know how many additions you'll have to do, could you think about how much you'd have to add each time in order to keep bridging the gap all the way to 162? It'll be interesting to kind of see how people eventually end up thinking about this, because I imagine that different people are going to be watching this and thinking in different ways. Unfortunately, in class, we would be able to talk about all the different ways you can hear other people doing things. But if you have the opportunity to, at least think about what way you're doing it. And if you have some time to reach out to a classmate, especially if you know somebody and you have their number or you're FaceTiming with them, it may be worth actually talking about how you're doing these pattern finding expeditions. Because you're probably noticing there's not really one right way to look at a pattern. Many people see different strategies in their mind's eye and communicate very differently and yet get the same answers. So if you have the opportunity to communicate to somebody with pattern finding in mind, it could be a good use of your time. And as always, if you're really not sure, or you just feel like you're not seeing any sort of pattern, don't hesitate to reach out via email, and I'll be glad to try to break down my pattern finding thinking as well. But with that said, let's take that 30 minutes of silent think, or 30 minutes, dear goodness, nobody's recording a video that long, 30 seconds of independent think time, and think for ourselves. How would we figure out the gap from 2 to 162? How do we figure out what's adding each time? And then we'll talk about how to put it into an equation. So again, 30 seconds of think time to figure out the pattern and to perhaps figure out the missing numbers. All right, wasn't that awkward? Still awkward. All right, so hopefully you figured out some logical approach to this and didn't just try to guess aimlessly for 30 seconds. I personally thought about the following bits of logic. I thought to get from 2 to 162, I would need to make 1, 2, 3, 4 jumps in the table, or in this list, I should say. So in each jump, I must be adding the same amount, because that's what makes it arithmetic. So my logic was first to figure out how much ground I need to cover to get from a 2 to a 162. That is a difference of 160 numbers, if I'm thinking about integers. So if I have to cover 160 integers in 1, 2, 3, 4 jumps, then 160 integers over 4 jumps makes me think 160 divided by 4. I must need to cover 40 integers per jump. So by that logic, I started thinking, okay, well, what if I did? If I covered 40 more integers in the first jump, I would be at 42. And if I cover 40 more integers, I'll be at 82. Cover 40 more integers, I'll be at 122. And sure enough, 40 more integers, I get to 162. So I can tell that that pattern worked. I definitely added 40 in order to connect the pattern and to make it work. So we know it's arithmetic because we added 40, and adding is an arithmetic operation. That also means that if we want to formalize things a bit, the adder, which again is the less grammatically appropriate way of saying the number that adds in the pattern is 40. And eventually you'll notice, because we're adding, we'll call it positive 40. If you're subtracting, it's appropriate to call your adder a negative number, because that's technically what subtracting is. It's just adding negative things. You could also call it a subtractor if you want to. But in keeping with the general structure of things, geometric sequences will have a multiplier, arithmetic sequences will have an adder, and you can adjust them as needed. Now, let's, while we're thinking about the pattern, consider what must have been before the first term. If the first term was 2, the number before it must have been the number that I could have added 40 to in order to get 2 as my answer. So again, you can think kind of like we did in letter A about thinking backwards. If I was adding 40 and got 2 as an answer, thinking backwards could involve maybe subtracting 40, just to think about maybe that inverse operation, so to speak. And I can infer that number must have been negative 38, because negative 38 plus 40 is 2, plus 40 is 42, plus 40 is 82, and so on and so forth. So in terms that now I need to kind of translate to an arithmetic pattern, let's talk about how to write an equation. Now that I know my important numbers, I need to format them correctly in an equation. On the previous page, page 2, in question number 21, you hopefully generalize some things about the arithmetic. Oh my, and I misspelled that word. How embarrassing. If you go back though, as I'm erasing this and just in shame covering up my own spelling error, if you go back to your observations on page 20, no, sorry, page 2, number 21, the wheels are just coming off here in this video, then you may have noticed some differences in the structure of an arithmetic versus the structure of a geometric, and maybe some similarities as well. In the arithmetic sequence, we still see that T of n equals notation. That's a commonality that we can definitely attribute to both types of sequences. And again, we'll get to why it's called that. For now, less of a concern. The arithmetic sequence also does have an initial value, but instead of parentheses to indicate multiplication, arithmetic sequences tend to have an addition sign. Makes a lot of sense. If geometric sequences are about multiplying, then their notation should suggest a multiplication operation. Arithmetic sequences suggest adding, and the notation that we always know is related to adding is a plus sign. Now, of course, it could also be a minus sign if you're adding or subtracting. So I'll put a little plus or minus there just to kind of indicate the fact that it could be negative if subtracting is needed. I'll just make that tiny little word if it helps. So we have an initial value plus or maybe minus, depending on the nature of your adder, the adder number followed by the letter n. Hopefully that was another observation that you made, contrasting your geometric versus your arithmetic. The arithmetic sequences do not have an exponent n. They have a regular standard sized n that almost looks like it's just attached to the number that generates the pattern, the number we've been calling the adder. So to formalize things here, arithmetic sequences typically do start with an initial value, and then either plus or minus, depending on the nature of the pattern, the adder with n attached, or times n technically. Now in terms of color coding here, I'll try to purposely kind of make the same choice of this blue. An initial value is an initial value no matter what kind of pattern you have. The initial value is always the term before the first one, if you look at a list of values. The adder is unique to an arithmetic sequence, so I'll color code it accordingly there. The adder is unique to an arithmetic because it's what makes arithmetic true. It's what makes arithmetic different than geometric. So to summarize then, we now know the structure of an arithmetic sequence. Let's see if we can translate question letter B accordingly. In question letter B, its equation will definitely start with T of n equals, just like all sequence equations will. And then we're going to borrow from the patterns that we've already observed about arithmetic equations in general. We'll start with the initial value, which we know is negative 38. Since my adder was positive, I'm adding a positive 40 throughout the pattern. I'll put plus, knowing again that that plus or minus depends on the nature of the number that generates the pattern. 40 was the actual adder number, or number that generates the pattern, followed by n. And notice again, this is a standard size variable n, not a superscript like in the geometric version of things. So now that you've seen the structure of both the geometric and an arithmetic equation, hopefully you can finish question number 27, because if you did letter C already, question letter D almost misleadingly looks like it's a duplicate of that question, but letter D is asking you to imagine the pattern being arithmetic. If the pattern is arithmetic, think about the pattern that connects you from a -4 to a -8 if you can only add or subtract, and then think about how that would generate the rest of the terms. Once you can identify the initial value, which is conveniently given to you, and the adder, then you'll be able to format this equation accordingly. Before you watch the next video, try to finish all of question number 27, including their equations, and try to check your answers. Once you know it makes sense, then the next video in the playlist will guide you through number 28, where you're kind of going to go in reverse. You'll be using an equation in order to help you predict and generate the number of terms.